Yeah, please start.
So is my slides visible?
Yeah.
Okay, so hi all, I'm Prajwal from group number 3 Avengers, and today I'll be presenting paper Flick Fast and Lightweight ISA Crossing Call for Heterogeneous ISA Environment. So the outline of this presentation will be like this. First, we will understand what the heterogeneous ISA system is and how the code execution is done in these systems and what kind of programming challenges we face. Later, we will discuss the Flick architecture, its implementation of various components, and then we'll evaluate some micro workloads on it. So let's first see what the heterogeneous ISA system is. So this system is the multi-processor system where on each processor the different ISA is get executed. So how does it benefits us? It benefits each ISA has its own beauty. The ISA like thumb has very good, very high code density due to its code compression ability. But drawback of thumb is floating point instructions are not available in thumb. So compiler has to emulate floating point arithmetic in thumb. In x86, register pressure is very low due to its various addressing modes, and x86 has good code density due to its variable length instructions. And also in modern system, there are various components apart from our main host core. These components are like general purpose processors, which has their own ISA, which is different than the host processor. So some of these examples are the NX with near X processors like Smart NICs and NVMEs and FPGAs. So these execute the different ISA than the host core. So in this presentation, we will in the example we will have we'll see that NXP is running RISC-V ISA and the host core will have x86 64-bit as its ISA. How this works is when in the execution of code, when we see that the certain region of our program is will give better performance if it is run on some other ISA, then we pause the execution of that thread on the host core, and we migrate the execution to the that specific ISA. But this gives a lot of this number of challenges in programming environment. The first one is that there is no generally widely accepted solution for software development. In case of GPGPU, we have seen that there are CUDA and OpenCL, which is widely accepted among the programmers, but there is no such uniform solution in this case. Also, the NXPs have its own private memory. So software development does not only need to take care of the communication between host processor and NXP, but also they need to take care of the data movements. And this is the extra overhead that software developers had to face. So there are some existing solutions that tried to tackle this issue, and those solutions had they had either the new operating system or and they had some modification to the existing operating systems. So what this existing solution assumed that they tried that each thread should be migrate at any point. So there was the dynamic profiling, and if you profile that the certain region should would run better in some other ISA, then the program migrate to that point. So this kind of solution includes the runtime binary translation, because the whole ISA is changing, and also the thread state transformation. So whole thread it register file and context is transferred to the other core. But this existing solution has lots of this overhead due to huge changes in operating system, and this thread state transformation is the huge overhead that we have to incur. So in Flick architecture, Flick assumes that the software developer is aware of the functions that are targeted to run at NXP, and also software developer is aware of the data that is associated with this function. So what software developer can do is he or she can tag those functions such that means they can be identified to run at NXP, and when in our program flow we encounter such function, then execution on host core will be stopped and this function execution will be migrated to NXP. So the major components in this Flick architecture is unified memory space, and the another is the thread migration, and later is multi-ISA binary generation. So we will take a look at the unified memory spaces. So what is says that all the virtual addresses should point to the same physical address for both NXP and host, and all the physical address should point to the same system components. It may be either the NXP private memory or the host memory. So what is saying that both the NXP private memory and host memory, we will see it as a combined unified memory, as if it is the single memory. And how it is implemented is on NXP the RISC-V ISE is running, and on host x86 ISE is running, but the TLB and MMU of NXP and host are identical. So both the TLB and MMU of both sides are identical, and they use same page table base register. So in this way all the virtual addresses from NXP and host will point to the same physical memory, and host can access the memory from the NXP via PCI interconnect. So here right side image, we can see that the view of memory from host side is like this. The host memory is from 0x0 to 8 megabyte physical address, and the private memory is seen from host side as the bar 0 region, and this region is dynamically allotted. On the NXP side, NXP views memory as it views host memory from 0x0 address to 8 megabytes, and it immediately allocates the NXP side memory to next addresses, which is from 8 megabyte to 10 megabytes. But we need that NXP should have the same view of memory as it is seen from host side. So remapping needs to be done on the NXP side to get the same view as that of host. So in such case, host passes the offset to the NXP TLB, and then NXP TLB adds that offset to the NXP side physical address to get the same view. The next component is the thread migration. So whenever we encounter the function that should run on NXP, the execution is paused at the host core, and that execution of the thread is migrated to the NXP. So how is it done is in x86 page table there is NX bit which is no execute bit, and if that bit is set and host try to execute that instruction in that page, then instruction page fault will occur, and the execution the operating system page fault handler will get called. So in this case what we will do is we'll set the NX bit in the pages where NX the functions that should run on NXP are stored. So when host try to execute the function that should have run on NXP, then instruction page fault occurs, then execution goes to operating system page fault handler, which receives which receives the address that of the function, and then it calls the user space migration handler, and this is the subroutine that is in the application binary. So this migration handler accepts all the function arguments, function address, and other metadata like stack information of the NXP um, and process ID, and then it starts the migration from the host to the NXP. So in right side image, we can see that first of all, host starts the execution, and when it reaches A, it encounters the function that should run on NXP, and then it calls the NXP function. Then it reaches the point B, and the function execution start at NXP, and at C, there is function which should be called on host. So NXP can also call the function on host, as a host can call function on NXP. So when at C, NXP calls the function that should run on host, and at D, host start executing that function, and at point E, host returns the data of that function, and NXP accepts it and continues the execution of the thread. And at F, when the function execution is complete, then it returns the data to the host, and host then resumes the execution of the thread that was paused. So here let's look at the pseudocode. First, we will take a look at when host try to execute function on NXP side. So here the any thread starts every thread starts execution on the host. So thread always starts on host, and first migration is always host to NXP migration. So we first of all we collect the in migration handler, we collect all the function arguments, and we check whether this migration is first migration or not. If it is first migration, then the stack on the NXP private memory for that thread is not allocated. So we first allocate the stack, and we then prepare for the host to NXP call by collecting the arguments and passing it, and then we migrate the thread and suspend that execution of the thread on the host core. And on the NXP side, this while loop starts executing on the right hand side, line number 5. When the host to call is on, then NXP fetches all the required argument, and then it calls the target function and collects the return data from that function, and then again along with the return data and some other metadata like the process ID, it migrates that data to the host side. And on line number 13 on left side, listing one, you can say that we can see that this host is accepting the return data from NXP, and then that return data is returned to the function call. So here we can see that execution, the function execution is transparent, as that would have happened if the function would have executed in the host core itself. In case of NXP to host, there are some changes. First change is that the condition for NX bit instruction page fault is changed. In host, we have seen that when NX bit is set, then instruction page fault occurs. In NXP side, when NX bit is 0, then instruction page fault occurs. So these are the little changes that we need to do in the operating system. And the other thing is, as the thread always start on host, there is no need to check whether the stack is allocated or not, because the stack is always allocated in this case. So in listing 2, in line number 3, we can see the execution is similar to that of we had seen in the last slide. The NXP prepare for the migration, and then it suspend its execution and migrate the execution to the host, and host executes this while loop and return the data. The next thing that is important is multi-ISA binary generation. So when we switch the ISA, the entire code code should be compiled for all the ISAs that are in our system. So what old approach was like, our entire software code was compiled to for each ISA and in a single binary file. But in Flick, we know that the certain function will specific functions will run on only the specific ISA. If it doesn't, then it will call the page fault. So these so these functions are compiled only for the targeted ISA. So let's look at the evaluation. The setup that is used for this evaluation is we use Intel's dual Xeon processor at the host system, and the NXP core is on the FPGA board, and FPGA the on-chip memory 4 GB on-chip memory on FPGA core acts as the private memory of NXP. And the PCI 3.0 interconnect acts as a bridge between the host and the NXP private memory, and also the connection between NXP core and the host core. So in the evaluation, we look at the what is the overhead in thread migration from both host to core and host to NXP and NXP to host. So we create the micro benchmark program, which calls the function on NXP and immediately returns. And we run that program again and again for say 10,000 times, and we calculate the average time taken for that round trip migration. So that comes out to be 18.3 microsecond. And if that's compared with the previous solution, then we see that there is huge improvement. It's almost 20 or the 30 times improvement compared to the previous solutions. And we also calculate the NXP to host round trip overhead. And how we calculate is that host calls the NXP function, and then NXP again calls the host function, and host that function returns immediately. And then then the host to NXP overhead is subtracted from the obtained overhead, and we get the overhead for NXP to host round trip overhead, and that's come out to be 16.9 microsecond, which is again very less compared to previous works. And we again look at one another evaluation, which is pointer chasing. This is the variable length linked list traversal. So here the context is that the linked list data is stored in the NXP's private memory. So we think that it would be beneficial if the linked list traversal function run on the NXP as it would be near to the data. So first we will run the benchmark with no migration interval. Means the host will again and again continuously call the NXT function. And here we see that when the linked list is less than 32, then the performance is worse than the normalized than the baseline. And baseline is what our baseline is, that when we have no NXP, when we do not migrate to NXP, and we have the execute whole program on the host itself. So we see that if the length of the linked list is greater than 32, then we start getting the performance benefit, and it later saturates to the when the performance is 2.6 times the performance that of baseline. And in the second in the right hand side chart, migration is done at the interval of 100 microseconds. So here most of the code runs on the host, and it does not frequently transfers the function to NXP. So here the major performance overhead is the accessing the NXP's private memory from the host core and not the
Prajwal,
migration overhead.
it's already time. Can you move on to the conclusion slide?
Yeah, so yeah, I'm almost done with my presentation. And yeah, these are all the images and the charts were from the first reference, which is Flick, which was the paper from
Yeah,
2020.
there is no need of references. We know that you are presenting this paper. Move on.
Okay, yeah, I'm done with my presentation and it's now open for questions.
Yeah, I don't think we can take questions now. If we get time, we'll take it at the end. Uh,
Okay.
Can the next presenter start presenting?
Hello.
If we finish everything maybe in 80 minutes, then last 10-15 minutes we can take the questions. But first finish it.
So is my screen visible? Hello. Am I audible?
No,
Now?
still no. Maybe in the interest of time, can we start from some other group? In the meantime, Rahul will try to set it up.
Yes, sure.
Yes, am I audible?
Yeah, perfect.
Yeah. Yeah,
Go
so
on.
good afternoon, everyone. So today I'll be presenting predicting performance impact of DVFS for realistic memory systems. So first, let us have a small look at what is DVFS. The full form is dynamic voltage and frequency scaling. So the major question we want to answer using DVFS is why run the processor at full throttle when your memory is going to slow you down anyways. So here is a small graph explaining that point. So over here, as we see, yes, yeah. So at this point, I incur a long latency memory miss. So from this point, what happens is whatever independent instructions were there, they will be executed. But then after a point, due to the lack of either independent instructions or the ROB being full, we are going to experience a stall in memory. So the idea is why not fill this gap somehow? So this image was taken by slides from Professor Biswa. And so there are two ways to fill these gap cycles. The first is to increase the number of independent instructions, which is not very feasible. But then the second way seems more correct, to slow down the processor so that the number of instructions is same, but then I'm taking a longer time to execute those instructions. So this is the way that we are looking to do. Now the state of the art DVFS controllers, they use something called as a two-phase view. What is this two-phase view? So this is an image describing the two-phase view. Over here, we can see that there are two phases, compute and memory. Now let us look at two major assumptions made by the baseline models. The first assumption is that all the memory accesses have same latencies. And by memory accesses, I mean here DRAM accesses. And the second assumption is whenever there's a DRAM miss, all the independent instructions are executed. And once there is a lack of independent instructions, the processor is stalled until the access is serviced. Now let us look at the state of the art method. So the first method is called leading loads. They define this P memory, which is the total memory access latency, and C compute, which is the number of compute cycles. Using this, they try to define the total amount of execution time as a function of the cycle time using this equation, which is T equal to C compute times C, which is the number of compute cycles times the cycle time, plus the memory access latency. And we get a graph like this, similar to Y equal to mx plus C. Now, there is another state-of-the-art method based called as stall time, which is a counter-based architecture, not too different from leading loads. But then this one is but then this one, what it does is it calculates the execution time based on the stalled experience using counters. But then there are some major shortcomings in the state-of-the-art method so far. So the first one is DRAM access latency was considered to be constant, but obviously it can be variable. Some of the factors because of which it can be variable is, first of all, there are row hits. If there is a row hit, the access time will be shortened. If there are bank conflicts, the access time is going to be longer. If I find some bank level parallelism, the access time could be shorter, and there could be some variable time spent in the memory queue, which may increase or decrease the access time. Another shortcoming could be because of streaming prefetchers. So for prefetchers, they introduce multiple main memory accesses for data to be used in the future. So this one will significantly increase the memory bandwidth demanded by the processor. So now to motivate the need for this proposal, I show you this graph. So initially using the constant memory latency, which was the assumption of the baseline, the state-of-the-art methods, the state-of-the-art methods perform decently well to whatever is the maximum ceiling that can be achieved. But then now when I thrust in variable DRAM latencies, I see that the amount of the ceiling is far away from what is reached by the baseline. And now when I throw in the prefetching as well, the baseline is very far away from what is the potential that can be achieved. So state-of-the-art DVFS controllers crumble under realistic DRAM models and prefetchers. So
Hey,
now,
just a quick question before we move on.
yes, sir.
How do you get this potential numbers?
So the potential number, so they use the method called as dynamic sampling. So what they did was they executed the program using different number of using all the different frequency points that they have, and
Okay,
for
got it.
every individual phase, they chose the one which gives the least power, the least energy. Sorry.
Yeah.
Yeah.
Okay. Yeah.
Yeah, so a realistic execution sequence may look like this. So over here, the first observation that we make is not all the loads are having equal latencies, and there are some write backs, there are stores, etc. And the second observation that the baseline made, that still stands, that independent instructions continue to fill the ROP during a long latency miss. Yeah. Now let us come to the proposal this paper has given, which is the first part of it is critical path calculation. So the assumption that they have made here is if two memory requests are serialized, it can be considered as a dependency chain. So now to do this, they have maintained certain counters. So the first counter is a global critical path counter. There is and because as the name suggests global, there is only one copy of this. Initially, it is set to 0. We also maintain individual counters. We maintain 32 of these counters for each for initiation of ith load. We maintain a counter named PI, which is set to the value of P global whenever the ith request is initiated. Now, after the ith load is completed, P global is updated using this given formula, which is maximum of P global comma Pi plus del T. I'll come to that in a moment. So now for this execution sequence that I had shown just earlier, let us look at how this proposal works. So initially, P global is 0, as I said earlier. When A and B, these two loads are set, when these two loads are initiated, PA and PB, two copies are created and both of them are initially put to 0, since P global at that time was 0. Now when load A finishes, what happens is P global will be updated to maximum of 0, A, which is A. Then what happens next is load C is initiated. So at this point, PC is created, a new copy is created, which is given the value of A, since P global at that time was A. Now when load B is completed, P global initially was A, but then the new delay was B. So P global was updated to B at this point. Now when load C is completed over here, because when C started, the P global was A. So Pi plus delta in that formula becomes A plus C. And since A plus C is greater than B, P global is updated to A plus C. So over here we can immediately see that two loads which are having overlapping latencies are just considered as one. Similarly, when D and E are initiated, the initial value of PD and PE are initialized as A plus C because P global was A plus C at that time. And then when D is completed at this point, it is put to A plus C plus D. And then when E is completed, the D is discarded because D and E are sort of overlapping at that point. And they have ignored the stores and writebacks because they are not going to stall the processor. Those will be counted as the compute cycles, as compute cycle. Now let us come to the second part of the proposal. So to motivate this, there is this. So they executed the application B waves for different amount of cycle times from 2 to 666 picoseconds. So over here, what we see is that as we keep increasing the frequency or as we keep decreasing the cycle time, the execution time or the time per instruction, it does not come down continuously. It saturates after a point. So the reason for this could be that the DRAM is not able to give data so quickly. So as I said, the performance saturates as frequency increases. This is because as DRAM latency remains constant, decreasing the compute period beyond the point will not result in better performance. So to model this, they introduce something called as a limited bandwidth performance model, or BW. So over here, they divide the frequency of operation into two zones. The first zone is the low frequency zone where DRAM can service prefetch requests before the chip stall. And the second one is the high frequency zone where DRAM is not able to service the prefetch request before the chip stalls. So over here, I'm going to model I'm going to model this as a piecewise linear type algorithm, similar to what Dvfs showed. So over here, the first part at a less than crossover frequency, that is at the high frequency, it is going to be the minimum memory delay. But whenever the frequency is lower than the crossover frequency or higher than the value of T crossover, it becomes the regular demand memory request time, which was T memory as discussed earlier, plus whatever time it took for compute instructions. Yeah. So now to calculate this T minimum memory, we need something called as DRAM slack. So T min memory is defined as the total memory access time minus memory slack time. So this memory slack time is defined as the extra time spent by DRAM so as to not violate any timing constraints. So to calculate this, there are counters at each DRAM bank, the DRAM bus, and the global DRAM itself. So now that I've said this, these are the hardware overheads for P global for each PI, the second one, and then three slack counters and one prefetch stall counter. Now they have given this experimental methodology where they have just said that they are using some x86 based cycle accurate simulator. They have not mentioned any names, and they have used MacPat and Cacti to model energy and power. Now they have used some policies for comparison. So as you had asked earlier, so first policy is static optimal, where they run it at all frequency points and they never change it during the execution. So if one frequency gives the least power for that application, that is chosen as static optimal for that application. Now this dynamic optimal, this changes because for each execution phase, they choose what is the lowest power for among all the frequency points that they have chosen. And that is, and all those minimum powers are added up. So this sort of gives me the ceiling. Now this third one is perfect memoryless. So for each execution interval, they choose the chip frequency that minimize the energy consumption for previous interval. Now results for energy reduction. So for these applications, which are memory intensive benchmarks without any prefetching, we see that the ceiling is around somewhere around 6 to 7%. These exact numbers were not mentioned in the paper, and we are almost able to reach up to 5%, up to 5.5% using our proposal. Then the next one is due to non-memory intensive benchmarks, where as we see in the scale, the ceiling itself decreases a lot to around 1%. Then the next one is prefetch heavy benchmarks, where the ceiling is around 7.5 to 8%, and we reach up to 5%. And the last category is non-prefetch heavy benchmarks, so prefetch light benchmarks, where again the ceiling is pretty low, and we are able to reach up to half of the ceiling. So a very interesting point over here is normalized power versus normalized performance. So what we want over here is the benchmarks, rather all prefetch heavy benchmarks which are mentioned over here, they should lie above the y equal to x line. If it is lying below that line, it means an increase in power is not giving me proportional increase in performance. So as long as it is above that y equal to x line, it means that our proposal is working better. Like for a little bit of extra power gain or a little bit of extra power loss, I am not experiencing as much performance loss, or I am experiencing a performance gain. An interesting example over here is the slip quantum, where the slip quantum lies in the second quadrant. So as I decrease the power, performance is somehow increasing. So this is an outlier sort of. So in conclusion, so previously proposed DVFS performance predictors, they oversimplify the memory system, and they are inefficient for realistic data models and for prefetching. And this method, CRIT plus BW, this realizes 65% of potential energy savings. So these are the references, and thank you.
You are so fast. We still have time, so we can take questions. We have 6 minutes. We can take questions for both the papers, both the presentations. So go on. Or there are no questions. Okay, so Avinav, do they talk about DVFS at the DRAM level?
No, sir, only for the chip.
Okay.
They have only meddled with chip frequency. They have all this time they have assumed that at DRAM everything is constant.
The frequency is constant. That's
Yeah,
what you
at the
meant.
DRAM.
Okay. And then what do you think if I change my DRAM frequency, will this model work?
If you change the DRAM frequency, actually you can come up with a better model, because we always need not have high frequency, right, at the DRAM end. For certain applications where we hardly access DRAM or there are very less memory accesses which are less memory intensive, we can actually reduce the DRAM frequency and probably try and gain some power benefits.
No, that's what it is already there in modern DRAM controllers, but I am talking about the model that they have proposed. In the presence of prefetchers, if you consider both CPU DVFS and DRAM DVFS, right? Will their definition of critical path and other things still hold true?
No, I guess the memory access times will change.
So that straight line part where for high frequencies, they are modeling it as like it is limited by the memory access time. So that giving it as a T minimum, right? T min memory. This part won't be constant now because it will also depend on what my frequency of DRAM is, right? So they cannot model this particular part as a straight line or a, I would say constant time, constant execution time.
Okay. 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 Yeah, if there are no questions, we can move on.
Thank you, sir.
Hello, hello. Yes, am I audible now?
You are better. Will you try for 10 more minutes with the hope that it will be even better?
I mean, I can't do anything more. I've turned off the
Okay.
fan and everything. So,
Okay. Okay. Yeah, we can get started. Sure.
yes. So, yes, is the screen visible?
Yeah. Yeah.
Thank you. So, hello, I'm Rahul from Team Cordump, and I'm going to present this paper, Clkscrew, exposing the perils of security, oblivious energy management. So, this is the outline of the presentation. First, we'll discuss some basic energy management system in modern devices. Then I will describe some basic aspects of the attack, and then we'll have a look at the attack on some attack demonstration on to find out the AES key in an environment. So yeah, power density in modern processors is increasing at a tremendous rate. So in this figure, you can see that the scale 1, 10 and 100, so it's rising exponentially, and still this graph looks linear. So, and there has been a lot of development in trying to manage energy and power, and so these have given rise to some security issues, so which one of which we'll have a look at. So when it comes to energy management, there are two kind of knobs that we can control. One is voltage and one is frequency. And power consumed is proportional to voltage times the frequency. So we have the freedom to kind of change each of these, and accordingly the power will change. Power consumption will change. So DVFS is a technique that is used commonly to manage power, uh, as the previous talk suggested, which, and this is the basic layout of DVFS. So there are hardware. In hardware, we have the voltage and frequency regulators. and these are controlled by memory mapped registers, over which we have the device vendor drivers. So every device has different drivers, and then the operating system drivers will kind of send the signals to this, and it will go down and so forth. So we notice here that software can actually control the voltage and the frequency of the device. So now, are there limits to the changes that are possible to voltage and frequency? The researchers have done this on a Nexus 6, which is cool because it is actually a real world device, and it's nice that they are doing it on these types of machines. And the maximum frequency that is advertised is 2.7 gigahertz. Now, in the graph, we see that the black points are what the device manufacturers are proposing as operating points. So the device only operates at these points. But when the authors of the paper, they try to change it manually, change the frequency and the voltage manually, we see that we get these blue dots where the phone actually crashes or reboots. So while keeping one of the parameters constant and increasing the other one, we see that this blue curve is actually the points where the device will crash, and this is an issue because this is not supposed to happen, but actually we can, through software, go beyond the operating limits. Yes. So firstly, there are 2 points to notice here. So there are no safeguard hardware limits. Through software, we can increase it by how much ever we want. But these are the points where actually the phone crashes. So there's no point in going beyond that. And if for some case we need to increase the frequency by a lot, which is not actually possible by the device, so we might reduce the voltage and then increase the frequency, which will have a lesser frequency than the original one. So this is thanks to this increasing curve here. Now, why does overclocking actually crash the device? This is because the digital logic actually takes some time to propagate uh, through the circuitry. So with a slow clock, and we know that these changes happen at clock cycle edges. So with a slow clock, when this will propagate, it has some time to reach the output. It's kind of like a deadline, but when we use a fast clock, such as this one, there is not much time, and it may be happen that it is disrupted and the output will still be the previous one. Now this is obvious for a 1-bit setup, but in a usual system with many transistors, this predicting what the output might be is kind of impossible, and hence we get those glitches and crashes. Now, is DVFS aware of trust zones? So in a CPU core, we have a trusted code execution zone, but the problem here is that a normal untrusted code can actually change the frequency and voltage regulation settings for the core, and even the trusted code will run with the same changed settings for voltage and frequency. So this can actually cause the crashes in the during the trusted code executions. So yeah, the answer is no. It's not aware of the trust zones. Now, why is this a really cool attack over traditional fault injections? Because we do not require any physical access and no specialized equipment. So this is an actual photograph from a fault injection attack I saw on YouTube. So yeah, we do not need any of this multimeter and anything. No oscilloscopes, nothing. And if anyone has ever tried to do this, they know how tough these things are. So yes. Now the challenges with Clkscrew are that we need to first find how high or low we can go with the frequency and voltage, which we have already seen a little bit of. And the other problem is self-containment of the attack on the same device as that of the victim. Now this is a problem because while the attacker is running, it might affect itself by changing the voltage and frequency. The solution to this is that the cores have different regulators. This is because development in DVFS has given very fine-grained regulators, and so the different cores have different regulators, and we can just pin the attacker and the victim on different cores. The other issue is that there is a noisy OS operating system environment where other processes might be running. I mean the authors, not me. And we need actually very precise timing to carry out these attacks, because I mean we can cause crashes and glitches, but that's not what we want. To gain real control over the device, we need to precisely have timing fault injection during the execution of the victim thread. So this is one of the examples that the authors have provided, that out of so many clock cycles of the victim, the fault was to be provided in 65,000 clock cycles of the victim, which is quite low, small as compared to this number. And so the solution to this is proposed that they are using high precision timing loops using no-op loops. And one more key factor here is that the trust zone allows measurement of execution time of trust zone executions from outside the trust zone. So we can actually measure and profile the execution timings of trusted code while it is running in the trust zone. So let's begin with attack one. Here we are trying to, this is a threat model. So there is a victim application running which decrypts EES and it executes in the trust zone. So this is the application. There is a secret key stored in the trust zone. And the attacker's goal here is to somehow derive the secret key from outside the trust zone. The attacker's capabilities are as follows. He can repeatedly invoke the app. So this, he can give it a ciphertext and receive plain text, and can control the voltage and frequency using software. So the idea behind this is you send it one ciphertext and it will give you the plain text using the, because we can call this how many ever times you want. And the next time we will send it a ciphertext, and during the decryption algorithm we will inject the fault, which will give us a faulty plain text. Then we can carry out differential fault analysis and derive the secret key. Differential fault analysis has some prerequisites that we require, which we will take care of in the future. And so this this method greatly reduces the key space of the key space, so that we can finally brute force the secret key and get this. So differential fault analysis needs Clkscrew to deliver a 1 byte fault to the 7th EES round. Now this, so now we need to actually find out when we have to deliver the fault. So they actually plot this graph. They execute the decryption app many times and find out what is the execution time, and we can see that most majority of it lies here. So there's not much variability. We know that we need to go inject the fault somewhere during this period of time. And how likely can we inject the fault in exactly one EES round? Again they try it out many times, and they find this that around 60% of the time we can find inject the fault in exactly one EES round, which is quite impressive. And again, how likely are we to corrupt exactly 1 byte? We need to corrupt exactly 1 byte in the 7th round, which will propagate, and then we can do some analysis, cryptographical analysis, to find out the secret key. And so again, here we see that out of those 60%, we can actually, about half of them are 1 byte, change 1 byte within the AES round. So these are the results for the experiments that they have performed. Around 20 faulting attempts were required to induce that one fault in that desired AES 7th round. And this took around 12 minutes on a 2.7 gigahertz quad-core CPU, which was the Nexus 6 that I showed you earlier. Now this greatly reduces the key space, as I mentioned earlier. It reduces it from 2 to the 128, because they were using AES 128, to 2 raised to 12, which is, I mean, we can brute force it in a couple of minutes. So now there was an attack too as well, but in taking time as consideration for this presentation, I have not done that, but it was also very cool attack and I recommend you to check it out. So why this attack is actually possible? Because there are no hardware limits on the regulators. So if there were limits, we could not actually cause the crashes. And again, the cores deploy different frequency slash volt are in different voltage domains. So we can actually target another core using our core. Hardware regulators operate across security boundaries, which is across trusted zones, and the trust zone execution can be profiled outside of the trust zone. So that's why this attack is possible. And so the possible mitigations are that we can limit the voltage and frequency changes and use separate regulators for boundaries. For example, trust zone, we can have a different voltage slash frequency regulator there. And they also recommend, the paper also recommends few software level mitigations such as randomizations. This is saying that you add few no-op loops in the execution of sensitive code, which will change the execution time, but there is a trade-off with performance, and so I'm not really sure about this one. And again, and they show and they also propose code execution redundancy, which is that they propose that you run the sensitive code multiple times and use some checksums to deduce that the actual what the actual output is. And again, there is a trade-off with performance, so I'm not so sure about this one either, but I completely agree with these hardware level changes, but they are difficult to implement as they are in hardware. Yes, thank you. That is the end of my presentation.
Okay, questions? There are no questions. Okay, then we can move on to the next presentation.
Yes, okay, thank you.
Yeah, it was good.
Thank you, thank you.
Hello. Hello, am I audible?
Yes.
Hi, good afternoon. So I
You
am
can switch on
Parasgar.
your camera if bandwidth is not an issue.
Okay. Sir, I am not able to switch on my. Give me 1 minute. Yeah. So good afternoon. I am Pascal and I am from Team 8 Kachra Set. So I will be presenting the paper Don't Forget the IO when allocating your LLC. So last week Hari told us about the DDIO, but as we already seen in the questioning that DDIO is not optimal for all the cases. So this paper tries to optimize the DDIO default case. And so to begin with, I will start with the background of the traditional IO and the DDIO. So what happened with the traditional IO, that there is an whenever IO packet comes to the IO controller, the DMA engine will take this packet from the IO controller and put it into the main memory. And when later CPU requires to process this packet, it will be fetched from the main memory to the CPU core for the processing. This is the good good mechanism to process the packet, but nowadays NIC is improving its bandwidth. So there are 40 Gbps and 100 Gbps NIC. So using this NIC, this system is not able to process the large number of packet. If we consider a case of 64 byte packet with 100 Gbps NIC, this system will throttle even at the 40 Gbps and it will not able to handle the 100 Gbps bandwidth of the NIC. So to improve the bandwidth and throughput latency, Intel proposed an architectural innovation in which what happens that whenever a packet arrives at IO controller, instead of putting it to the main memory, it will be directly put into the two default ways in the LLC. And these two default ways generally the last two ways, way n minus one and way n. So from this packet, CPU can directly fetch the packet and process it. So this will improve the latencies and it will also decrease the memory bandwidth consumption for our IO processing. But this DDIO is not optimal. It has two major problems. One is the leaky DMA problem. So whenever the input data rate is greater than the CPU core processing rate. So this generally happen with the small packets. So whenever the there are large number of small packets, so within the same bandwidth we get large number of packets. So let's say that our current LLC default 2n minus ways and n ways are currently full. So whenever more packet arrives to the LLC, we need to put into the LLC as per the default configuration, but there is no space for this default package. So we need to move some packet to the main memory from the LLC, and after that, when our CPU wants to process this packet, it will be again fetched from the main memory to the CPU cores. And when we are again fetching this packet from the main memory to the CPU core, it can be put into the either of the CPU LLC ways. It is not necessary to put into the n minus and n ways when we are fetching from the main memory. So it will incur extra read and write bandwidth because now we have to again put back into the main memory and fetch from the main memory again, and we have to handle the cache allocation and deallocation. And it also increases the packet processing latency as compared to the default baseline DDIO case. So to solve this problem, we have that we can use the small buffer sizes. So using small buffer sizes, what happens that we can allocate more buffer in the same space of the LLC. But this is not optimal, as we can see that when we did so in the graph 1, when we tries to reduce the packet size from the 1004 bytes to 512 bytes, we see that processing throughput of our system decrease, and it decrease even more when we further try to reduce the packet. But as we can see, the throughput of the bandwidth generally for the large packet as up to the 256 byte, this throughput doesn't decrease much memory bandwidth. But when we further reduce,
Hey, I think you are wrongly saying entries are bytes. The x-axis is the number of entries.
sorry, number of entries. So when we further reduce the number of entries, it decreases the throughput further. So using this small buffer size, so there are two problems with this solution. First is that because we are using single receive TX buffer for all the application on the server, so each application will get only few entries in the default receive TX buffers. Second, it will decrease the throughput of our system. Another problem with the system is that so using Intel cache allocation technology, we can allow our application to use a single LLC way in the shared LLC. So, but whenever we incorrectly allocate a cache way to the application, so let's say a application also using the n minus way and DDIO controller is also using the both two ways. So it will increase the contention between the application and the DDIO request. So increasing the contention can incur up to 32 performance degradation. So we need to handle this case also when application is contending with the IO controller, DDIO controller. As you can see that in the graph, so this is the application which is XMEM. So what XMEM do that it process the packet from it serves the cache data from the main memory to the application. So when we increase the working set of DDM, when working set is increased, so it will take more space in the two default ways in the DDIO, and we can see that throughput is decreasing when there is an overlap with the DDIO, and also average latency is also increasing for these two cases. So our problem statement is the LLC is very critical hardware, and allocating LLC to the different application can improve the performance of our application, and it can improve the quality of service. So to improve the quality of service, what Intel DDIO did that it injects the IO traffic directly into the NLC. But the default configuration, as we already look, it is not optimal. It deals with the two problem, leaky DMA and latent contender. And as we have to see, it can incur up to 32 performance degradation as system without DDIO. So what author do that? It tries to improve these solutions. So author provides a solution called IAT, IO Aware LLC Management. So what it authors do solution is that it monitors the LLC miss that occur because of DDIO traffic in the default configuration. So when we saw the increase in the miss, so either this increase in the miss maybe come from the DDIO traffic, IO traffic, or it can come from the application traffic, because application is now required more data in LLC. So what IIT do that after it determines whether this miss is caused by the core. Core means application running inside a core, or the DDIO default configuration. After that, it analyzes the, so to determine this miss cause, which caused the miss, it needs some performance count, it needs some mechanism. So to analyze this, what IIT do that it use the performance counter in the hardware and find the state of the current system, and using that state it dynamically allocate more or less way for the DDI. So what IIT can do that it can now increase the LLC way for the DDI, or it can decrease the LLC for DDI dynamically at the runtime. So to find the which application caused the miss, it needs some performance metrics. So DDI use three types of performance metric. First is the application type performance metric. So it tries to find whether the application is giving the quality of service or not. So to calculate this, it is using the instruction per cycle. So how many instructions are executing for a given cycle. Second, it is finding the characteristics of the cache and the main memory. So to find this, it is using the LLC references and the miss count. So if we have higher LLC reference mid count, then we can assume that our system is not performing optimal. So we have to make a chance some decision and either allocate more LLC way to the DDIO or core. Third, it is so to find whether we have to allocate more LLC ways to DDIO, it find the DDIO status also. So DDIO works in the two way. So first is DDIO hit, when we have already space in the LLC way and we can directly put the incoming packet into the LLC. So it is called DDIO hit. But when there is no space in the LLC default configuration, we need to update, make way into the LLC. So it is called the DDIO miss. So using this performance counter, what IIT do that it find the current state of the system. So there are 5 states in the LLC state transition of the IIT. So first is the low keep, when application has the required number of DDIO LLC ways allocated to the DDIO and it is performing optimally. Second, when we saw the increase in the DDIO miss, so because DDIO miss is increasing, we can assume that it is occurring because of the IO intensive application. So we assume that we need to give more LLC ways to the DDIO. So what current system moves to the IO demand state. Similarly, when we saw that there are large number of DDIO hit, when the DDIO hit is also decreasing and DDIO miss is also decreasing. This is because when DDIO hit is decreasing, we can assume that there are no incoming packet, and DDIO miss is decreasing, that DDIO has enough space in the LLC. So we can assume that this is the application requires more core, more LLC ways. So we move the current state of the system to the core demand. Also between these two states, what can happen that dynamically more IO requirement can come and more core demand will came. So what IIT do that it will get some LLC base from the DDIO and it will move to the low keep state, either to the high keep state. High keep state is the when maximum DDIO base can be allocated to the DDIO configuration. So how IIT is implemented? It is implemented as a user space driven process in the kernel, and to find the performance counters and the change this value, it is using the x86 MSR registers, basically read MSR and write MSR, and using that it is getting the values from the hardware and setting the value in the hardware. And finally, to allocate the LLC ways to the cache, it is using the Intel cache allocation technology to give a application to give the LLC way to a particular application or the DDIO. So let's see an example of DDIO. So here we have the this is the our LLC, and it is divided into 10 slices. So initially an application running inside the core has 3 LLC ways, and the DDIO has 2 LLC ways, and 5 LLC ways are not allocated to any application. So when we see a fewer DDIO hit, it means that IO demand is increasing. So we need to increase LLC ways for the DDIO. So it allocates 2 more LLC ways to the DDIO, and the system will remain in the same keep state. Now when we further see that these DDIO miss are decreasing and hit also decreasing, so we can assume that we don't need to give more LLC ways to the DDIO, so we can reclaim some of the waste from the DDIO. So system will take one way from the DDIO and it will make it unallocated. So to verify the system, what they are using, that they are running an application. So to test, because we are working with IO, so either we can do the disk IO or we can do the network IO. So what they are doing, that they are using a system with 2 NIC. NIC 1 and NIC 2 both are the 40 Gbps NIC, and using the virtual switch OVS, they are running 2 applications inside 2 containers, and in the container what they are running, that they are running a test PMD application. Test PMD is an DPDK application which diverts the packet from the layer 3 to another machine, and in the OVS there are 2 default tools are set up. That one NIC will only communicate with one container, and other NIC will communicate with another container, and for both container they have allocated 2 cores for processing of data. So we can see that initially when the packet size is small, so we can so our default configuration has enough size to process this packet, and further when we increase the size, we find that it is default configuration, and the IIT also provides the same packet. So but when we further increase the packet to 512, so default configuration of a DDIO, 2 LLC ways cannot be able to handle all the incoming packets, so we need to allocate more LLC ways to the DDIO. So when the system came to the state of 512 packet size, IIT allocates more LLC ways to the DDIO. So using that, as you can see that for the IIT case, our hits are increased as compared to the baseline, because now DDIO has more LLC ways as compared to the default configuration, that is 2. And further we can see that it is further increasing the performance of the system. So we can assume that allocating more LLC way to DDIO leads to higher DDIO hits. Second experimentation is they try to solve the leaky DMA solution. So as we already see that when we are trying to increase the packet size from the 64 to 128, so this leaky DMA problem doesn't occur. But when we further try to increase the packet size to 256 and 512, this leaky DMA problem start occurring. But because IIT has allocated more LLC ways to the DDIO, we can see that we are seeing lesser bandwidth penalty in case of IIT as compared to the DDIO, because now we have to put less packet from the cache to the main memory as compared to the baseline, and they have experimented that using IIT we can reduce our bandwidth consumption by 15.6%. Third case is they are trying to solve the latent container problem. So because OVS is an application running in the Linux kernel also, so OVS, we can consider OVS as an application which is sharing with the DDIO. So what OVS do, that it maintain the flow counts of the different application and it redirects packet from the one application to other. So when we saw that we increase the packet size, so there is a default contention between the OVS and the DDIO ways. So but as we can see that when we increase further, we can see the cycle per count reduce, because now what IIT do, that it increase the LLC ways for the DDIO and these cycle per count. So cycle per count is the how many cycles we are taking for processing packet. It has these are further reducing because of IIT. So now there is a question came that how much resource this IIT is utilizing. So what author did that they have tried to find the IIT overhead. So to find the IIT overhead, we need to find the state of system. So currently when we change from one state to another state, that is, let's say that we move from the reclaim to the IO demand state. So cache will take some time to change. Cache will take some time to show the changes. So either our system can be the stable state that when we need not to reallocate the LLC, and system can be unstable state that we are seeing changes in the performance counters, but because we have recently changed the LLC ways, we cannot currently change the performance count the LLC way because cache is changing. So when we try to increase the number of tenant is the number of application running in the containers. So when we try to increase the number of application in the container, you can see that performance overhead for the IIT is increasing, but it is not increasing by 800 microsecond even when we are running 16 tenant in the same application. And what they did that they tried to run this at IIT and the application with the same code. So we can see that with the contention also we are not getting more than 800 microsecond of execution time. So we can see that execution time of IIT is negligible. So conclusion is that default DDIO configuration is not optimal. So we need to optimize this. So to optimize this, author proposed the dynamic allocation of LLC waste, and we see that it decreased the memory consumption of bandwidth by 15.6% as compared to the baseline configuration of DDIO. And also for the latent contender problem, they reduced the performance penalty by 10%. So, and also author, I have skipped some part. Author tried to mitigate the performance interface caused by different applications running with the DDIO. Thank you. Any questions? Hello.
Yeah, I guess no one has questions.
I have a question. Am I audible?
Okay, there is a question.
Yes.
Yes, Paris, in slide, I think 13, you probably mentioned that it is checked, yeah, here, yes, that it is checked that how many LLC ways are not allocated. Did I hear it correct?
Yes. So what author means that so they try to measure the performance benefit. So they run the DPDK application in one container and they try to find the performance benefit also. So they allocated to LLC base for the DPDK container and three LLC base for the DPDK container and two LLC base for the DDIO default configuration. And the remaining LLC base we can say that they are unallocated. Maybe they are allocated because to the other application or the Linux kernel, but according to the user example, these are unallocated. Am I clear?
No, I did not understand. So you are saying that, let's say if on a core an application is running and also there are some DDIO packets coming. So both of these are restricted to some of the ways in the LLC. Is this what you mean?
Yes.
Okay, and then there are some ways which are unallocated. Okay, so this is done intentionally. And after
Yes.
that it is allocated that which one will be provided more LLC ways.
Yes, later they find what are the current situation of LLC using the LLC miscount, and after finding the LLC miscount, they move to the either state in the 5 state of the state transition diagram, and using that they decide whether we have to increase the more LLC ways for DDIO or more LLC way for the application running inside core.
Okay, so is it a kind of initial state for IAT? Is it correct to say?
Yes, initial state will be the default configuration where two LLC ways are allocated for the DDIO.
No, then when this state will arrive, where the core application is also restricted to few of the ways, and so is the DDIO packets are restricted to some of the LLC ways.
I didn't. Can you repeat?
Okay, I'm saying that when will this LLC state arise where the core application and the DDIO packets are restricted to few of the ways in LLC, and then there are some unallocated ways in the LLC?
Right.
When does this situation arise?
So using this, so, so what IIT remain, so IIT can be in the 5 state in of out of these. So what IIT did that. So let me go to the one extra slide and I will. So this is the execution flow of the IIT. So when initially IIT starts, so it will get the information of the what are the current state of the LLC and which ways are allocated to which application, which ways are allocated to the DDIO. Then later it initializes the system and allocate LLCs to the Docker container they are running and default configuration for the DDIO. And later when application start running and package start coming to the DDIO to the our system, it will continuously check and find the performance data. So it will come, so after every few seconds it will pause the system and it will check the performance data and check whether the performance is stable. So stable means that we are getting the optimal performance that author has decided according to their baseline. If not, we need to move to the either of the sum state that I have shown. If that, so when we move to a particular state, we need to allocate more LLC way to that application or DDI, and after that it will again go to sleep and again the process continues. So this cycle continues repeatedly. So every time after every few seconds it will check the current state of the system and it will predict what might be the state of the system and allocate more LLC way to this program. Am I clear?
Okay, I'm clear with this diagram, but in the previous diagram where you have those unallocated ways, so those are kind of taken from either DDIO or from the core application, is it?
No, they are not allocated to any of the core or the application. They might be allocated to the kernel also, because there are some other application running in the system. So for our scenario, we can consider them as unallocated, because we are testing with one container and two LLC is allocated for DDI. Remaining we can assume as unallocated.
Okay.
Because another application might be running in the system, let's say our browser is running, so they might be using these LLC ways, but we can reclaim these way to improve the performance of our default containers, because main motive of the system is to improve the quality of service for the containers.
Okay.
Yeah, Sika, this allocation is done for a particular core, not for all the cores. So the unallocated here means there are other cores which are using those ways.
Okay. So yeah, so this also, I also have one more question. What will happen in a sliced LLC? Because this question is arising from the concept that the slices which are near to a core, those cores data will be mapped to mostly will map to the nearby slices to that core. So in that scenario, how does this this partitioning for DDIO will happen?
As you already know that the addressing mechanism of the slicing of LLC is not available to the programmer, but Intel provides an API. Let me find that API name. So using that API, we can consider that we can allocate few LLC ways to the application. It is guarantee of that API is that we can allocate only complete LLC way, not the partial LLC way to a particular application.
What partial LLC? What does it mean? What are you saying?
So let's say we want to allocate same LLC way, let's say this third LLC way to two application. So we cannot do that using that Intel API, but we can allocate one LLC way to the particular API. But how actually it is implemented hardware is not visible to programmer.
No, her question is different, right? She is asking about LLC slicing. She's asking in the presence of LLC slicing, where you have multiple LLC slice, how does this allocation happens?
I'm not sure how it is happening in hardware.
Okay.
They have said that we are assuming that the cache is using Nuka architecture, that is non-uniform cache access
Yeah, that
architecture.
is slices. Nuka is actually sliced LLC. Yeah.
Okay.
Yeah, Yasika, I don't think they have all this slice hour allocation. This is just way based.
Okay,
So
okay, but
once you decide a particular way, that is allocated in all the slices. I think that's what it is.
I mean there might be that few of the packets get mapped to farther slices, and then there will
Possible,
be more
possible,
latency.
possible.
Okay. Yeah. Okay. Yeah. Thank you. Thank you, Mr. Thank you, Paris.
Thank. Can I stop sharing?
Yeah. There was
Okay,
a
thank you.
stop the recording also.
It is.
Are you done? There was this.
It is stopped.
Okay. So any questions for Thursday? Any query? Anything that is not clear regarding the presentation?